Welcome back. Now we're going to take a look at an application example of the linear or integrating factor method. This is example 2.3.7, which follows directly from 2.3.6. Now in the previous example in the book, the tank took about 27 minutes to reach the desired concentration of 1 gram per minute. This is salt within water. Let's speed up the process by increasing the inflow to 2.5 liters per minute, keeping everything else the same. Can we reach the desired concentration of 1 gram per liter before we overflow the tank, which has a maximum volume of 160 liters, starting at 150 liters? That's our goal. So we start out with the conservation model. After we've drawn our diagram, this is following the diagram in example 2.3.5, showing the mixing going on in the middle, initial conditions for X, the salt amount, and the volume, as well as the inflow rate, the concentration in rate, and the outflow rate, and the concentration out rate. This is the only component of our diagram that is unknown. We have an unknown X, amount of salt going out, and unknown volume because it's changing. We're changing the input. So for the conservation model, we start out with the rate of change, material change, equals the rate in minus the rate out. So our X prime, the rate of material change, is equal to some amount of flow in times the concentration in minus some amount of flow out times the concentration out. So let's use a diagram to fill in the blanks. Flow in, liters per minute, 2.5. Concentration in, 3. Flow out, 2 liters per minute. Concentration out, X over V of T. Well, to find out that volume, we need to take the initial volume of 150 and then add the net flow rate. Flow rate in is 2.5. Flow rate out is 2. All that times T, giving us 150 plus 1/2 or 0.5 T. I'll write that as T over 2. Okay, so let's fill that in. 150 plus T over 2. Okay, so now let's simplify the equation down. First, checking the units. Our X is in terms of grams. Our prime is in terms of time. So whatever time unit we're using here. In this case, it'll be minutes. We'll want to track the change in minutes. And then our rate in has the liters canceling, leaving us with grams per minute. Here, the rate out has liters canceling, grams per minute. So yes, our units do check all the way across. So we will write down the simplified version, 2.5 times 3, which is getting us up to, well, think of this 2.5 as 5 halves, so that's simply 15 halves, or 7.5. And then we subtract 2 times X all over 150 plus T over 2. That's a lot of compounded fractions. So I'm going to multiply the top and bottom of this fraction by 2, giving me 4x divided by 300 plus T. It just simplifies it a little bit. It'll help us a little bit with some of the derivatives going forward. And don't forget, our equation comes with an initial condition of 20 grams. Okay, so there is our model equation we want to solve. Now let's make some room and solve it using the linear method. Let's first check that we can solve this, I suppose. It has that. First, we have our unknowns, x prime and x, show up to the first power. So the unknowns are first order, or the unknowns show up to the first power, which means they satisfy the power condition. They are not multiplied, and we'll try to add them in a way that will satisfy the form x prime plus p of t times x equals q of t. So it looks like it is linear so far. Let's verify it here. X prime plus 4x over 300 plus t equal to 15 over 2. Okay. If we factor that x out, there we have the form with p of t being 4 over 300 plus t. So that is linear. Check. First step, we compute the integrating factor e to the integral of p of t, which is our 4 over 300 plus t dt. Okay. Well, this looks similar to some log problems we dealt with before, so let's use a u substitution. In this case, du and dt are the same. Very nice. Giving us, and to help things out, I guess we could bring the 4 out. Giving us e to the 4 integral of du over u. Now we get our log on the top, e to the 4 log absolute value of u, plus a c, but since we are only needing one integrating factor, we can drop that c to find the simplest form. I choose c equals 0. And let's simplify it down a little bit. Write that as e to the log of absolute value of, what is u? 300 plus t. If we want to get rid of that 4, we can move it by the log properties up on top to the 4th power. And now e and natural log cancel each other because they're inverse functions, leaving us with the absolute value, which, by the way, if our time is positive, that is simply 300 plus t to the 4th. Okay, so there's our integrating factor. Let's now take some room and multiply through by it. By the way, notice that we will have 4 powers of this 300 plus t multiplied through, and one of them will cancel with that p of t, leaving us with 3 of them, 3 powers, or 3 copies, I should say, times x equal to 15 over 2 times all 4. Okay, now let's check to see if the derivatives match up. If we take the 4th power of this combination and we take the derivative of it, we use the power rule, bring the 4 down, reduce it down to 3, and then take the derivative of the inside in terms of t, which is just 1. It's perfect. So we get our integrating factor, 300 plus t to the 4th, times x, all of that, the derivative, equal to, make some room, 15 over 2 times the integrating factor. And now we will go through and integrate both sides in terms of t. And you know what? Since we have a constant, let's just sneak that integral around the constant. On the left-hand side, it's as easy as can be using that fundamental theorem of calculus to undo the derivative. We'll get a plus c and throw it onto the other side, as usual. On the right-hand side, we're integrating something raised to the power. And this is actually the same kind of u substitution we just did up here. We can actually use the same u, believe it or not. And that will give us constant 15/2. We have u raised to the 4th power. When we integrate that, we will raise it up to the 5th power and divide by 5. So we get u to the 5th power divided by 5 plus a c leaving us with a 3 on top. And then finally, we can solve, well, first let's write that in u in terms of t. We have 3/2 times 300 plus t to the 5th power plus c. And now we can solve for x. We divide by 4 copies of the 300 plus t. We have 5 copies right there, leaving us with 1 copy. 300 plus t. And then we have the c divided by 4 copies, which inverted gives us plus c times 300 plus t to the negative 4th. So before we apply this definition, this is our general solution. Okay? So let's just check real quick to see if it makes sense. We start at time equals 0 with 3/4 of 300, and we're adding some multiples of 300 to the negative 4th. Well, I'm hoping that's going to be a negative quantity to bring some of this down a little bit, because our concentration should be starting around 20. So we'll have to see what the value for C gives us to make this work. So let's clean up a little bit. Erase that. Okay. So now let's apply that initial condition. And once we have that specific solution, we can answer the question. If we can reach the desired concentration of 1 gram per liter, so X over V of T, if the tank can only hold 160. So we want to see if we can reach the desired concentration before we run out of room. So if we plug T equal to 0, we get 3 halves of 300 plus c, this is a negative 4, c over 300 to the fourth. All that is equal to 20. Okay, so let's solve for c. We get c over 300 to the fourth is equal to 20 minus 3 halves of 300. We're going to be multiplying by 300 to the fourth. This gets a little bit complicated here. So let's see if we can resolve it a little bit further. Times 300 to the fourth minus 3 halves of 300 to the fifth. So before we try plugging this in our calculator, let's see if there's anything that we can factor out some common terms. I would say 300 to the fourth seems pretty common. We just multiplied it through, but maybe we can resolve it. You know what? We just did that. Let's back up a little bit. Let's resolve what this expression is and then multiply by 300 to the fourth. I like that idea. Since it was the only thing that we can really factor out. So 3 halves of 300 gives us 3 times 150, or 450 there, subtracted from 20 is a negative 30. Okay, can we resolve that a little any further to help us out? Well, let's see, can we factor out powers of 10? A negative 3 times 43, no, a negative 3 to the fourth times 43 times 10 to how many? Well, we have 1 here, we have 2 copied 4 times, that's 8 more. That's a fairly sizable value. Okay. So let's see how it fits together. Now let's quickly see, is there which form is most simple to plug c into? Well, c is multiplied by something to the negative 4th power. And you notice that when t equals 0, we end up having a 300 to the 4th on the bottom. So maybe this is the simplest form to write it so that we can check that when t equals 0, it knocks out the 300 to the 4th. Maybe that's it. So 430 times 300 to the 4th divided by 300 plus t to the 4th power. So that is our specific solution. Okay, so now we want to answer the question with it. A desired concentration of 1 gram per liter relates to X, the solution we found, divided by the volume. Now recall, V of t was 150 plus t over 2, or 300 plus t, all divided by 2. So, we're going to use this V of t, divide it through into X to get our concentration, set that equal to 1 to solve. Let's clear up a little bit of space again. Reaching desired concentration, X of t divided by V of t equals 1. So we take our X divided by 300 plus t divided by 2. So that will cancel out this 300 plus t divided by 2, leaving us with a 3 here. I'll write it right above here. 3 from this term. And then we subtract. We have 430 times 300 to the 4th. We are dividing by 300 plus t. We already have 4 copies we're dividing by, so that's another copy. The 5th, check that again. And then we're also dividing by a 1/2, which means we're multiplying by 2. And all of that is equal to 1. So let's resolve this. First, we have 3 on this side. We're going to subtract 1. We're going to add this negative component over. So that's 2 is equal to this 2 times 430 times 300 to the 4th, all divided by 300 plus t to the 5th. Cancel the 2's. And then we're going to, let's just do a 1 here now. Multiply both sides by this component and resolve that down. So more room. (300 plus t to the 5th is equal to 430 times 300 to the 4th. We take 5th root. And t is equal to 5th root of 430 times 300 to the 4th. All of that subtracting 300. Now we can use our calculators to approximate this construction, because we can't resolve it. There's no obvious 5th powers in there. And that gets us down to 22.4 minutes, which is less than the previous 27 minutes in example 2.3.6. That's great. That's good. Now the question is, when does the tank fill up? This is actually a much easier question. We probably could have answered this at the very beginning, but we didn't really need to know until now. The tank fills up when V, which equals our 300 plus T over 2, making some room, is equal to 160. So we resolve. 300 plus T equals double 160 is 320, which means that T is equal to, subtracting 300, 20 minutes. Wait a second. The tank fills up in 20 minutes by increasing the inflow rate 2.5. But we don't reach our desired concentration until 22.4 minutes. No! So, we didn't do it. We tried to increase the rate to get the process to speed up, but we obviously guessed wrong, and the tank filled up before we were able to reach that equilibrium. So, no. Tank fills up before desired concentration. A follow-up question to this could be related to, well, what is the fastest you can increase it to get the shortest time without overflowing the tank? Perhaps that's for another day. But do notice that as you change that inflow without changing the outflow, the imbalance creates a quite a bit more complicated problem to solve than it was in 2.3.6 when you have those that constant volume. So we made it through. We were able to answer the question. No, we didn't do it. We couldn't get to the 1 gram per liter. But now we know how to get through the process and perhaps tweak that inflow rate back a little bit to get to our desired concentration without overflowing the tank. Maybe we just need a bigger tank. Who knows? Okay, that's all for today.